Okay, cool. Welcome everyone to the first UTIG discussion hour of the semester. Thank you for showing up on Zoom. I hope you're all staying warm and safe at home. And yeah, we're excited to have Julian Lowman here, and I'll let Torsten give a more formal introduction.
Thanks, Mackenzie, and thanks, Hunter, for giving us a chance to discuss the science here. It's my pleasure to introduce Professor Julian Lowman. Julian is a geodynamicist who has worked on a number of global and regional dynamics problems, including the effect of continental cover on heat transport and how convection makes plates in viscoelastic rheologies. He got his bachelor's from Toronto University, his PhD from York University, also in Toronto, and then did a postdoc at Los Alamos, was a lecturer at Leeds, and joined the University of Toronto in 2006, where he's been an assistant associate and then full professor. Julian was kind enough to came by, visit us this week, getting sort of a slow start thanks to the snow, but he'll be on the main campus tomorrow, meeting with some of you, and then he's going to be at UTIC Thursday and Friday. So please be in touch if you haven't already, if you want to meet with him. And I'll hand it over to Julian, who's going to talk to us about the generation of plates for mantle convection using Euler poles to identify and analyze plate evolution. Thanks, Julian, for joining us.
Well, thanks very much, Torsten, for giving me the opportunity to come down. Wanted to start this off, as I would with any talk, with just also mentioning everybody else who's been involved in the work that I'm going to present here this afternoon. That's Joshua Guerrero, who's currently postdoc at Academia Sinica in Taiwan. Joshua's a former PhD student in my group at Toronto. Paul Tackley, some of you may be familiar with Professor Tackley's work. He's at UTIG Zurich. Sean Langemeyer is my former PhD student. I'll present some of his work from his thesis. And Pejvak Javahari is a current PhD student of mine. And finally, Chad Fairservice is a senior undergraduate with me. And Taiwo Ojo was a postdoc in my group who has moved on now back to atmospheric physics, where he started. So in thinking about how to start this off, a sentence came to mind the other day, which I jotted down trying to write the introduction for a paper. And I thought, okay, a series of questions might put us in the right frame of mind for understanding some of what we really need to get to grips with here. So I've said, when has a mantle convection model generated plate tectonics? It's really not such a trivial question as we might think. The sentence I wrote down was this one: ever since the numerical modeling of momentum-free convection became feasible, geodynamicists have been investigating the system and fluid properties required for generating plate-like surface motion. So it occurred to me that there's kind of a conflating of two ideas potentially here, trying to generate plates versus trying to generate something that looks like plate boundaries. So I wanted to kind of discuss those two issues separately to start with, and ask some more questions like, what should we be striving to model? So I thought, well, we want a generation of, let's say, a dozen-ish regions, and we would say these should each be moving rigidly and distinctly relative to each other. Those would be something like plates. What are the signatures of that behavior? Well, it's rigid body rotation about an axis through the sphere's center. And this may seem intuitively obvious to everybody, but if you had your mindset based upon looking at the literature or doing any modeling in Cartesian geometries in the past, that can set you a little bit off course. So I want to talk here today a little bit about what does it mean to get rigid motion on the surface of a sphere. Is there anything else specific to plate tectonics that we should worry about? Well, there's the appearance of three distinct types of plate boundaries on the Earth. We don't just have two, right? The good thing about modeling in 3D is that not only can we expect to get the convergent boundaries associated with subduction and the divergent associated with ridge axes, but also we should be looking for conservative boundaries, which we associate with transform faults. And then something very high on the wish list in terms of modeling terrestrial mantle convection with plate tectonics is to get one-sided subduction. I'm not going to say a lot about that, but I might be able to return to that idea a little later if time permits. Something else that is a real issue that has to be accounted for in the models is a relaxation perhaps on the requirement of only focused plate boundaries. If you dig into the tectonics literature, you see constant reminders that about 15% of the Earth's surface area doesn't fit so neatly into either being a rigid plate or a plate boundary, but rather may be deforming. So that means when we are modeling and trying to generate plates, perhaps we can give ourselves a little bit of leeway if we get somewhere between 10 and 20% of the surface not being a tightly focused boundary. And again, we'll see some examples of what I'm referring to as we move forward. So what are the parameters that actually impact the generation of plates? The parameters that we're going to discuss here. And I can present arguments for why all of these things matter. It should hopefully become apparent, but feel free to ask me at the end if anything wasn't too clear. There's the system parameters. So obviously there's gravitational acceleration and the depth of the mantle. There's also the geometry of the mantle, by which I mean the radius of the core, or perhaps more specifically, the ratio of the radius of the core to the radius of the planet, which is often denoted as F in the literature. There's also the fluid dynamic parameters. There's the thermal expansivity, alpha, the thermal conductivity, K, the specific heat at constant pressure, some sort of a reference viscosity, and similarly some sort of a reference density. The other thing that has to go into mantle convection models from the outset are specifying information about boundary conditions. I should also mention that we have to model internally heated convection if we want to model something that's like terrestrial convection on the Earth. And so there's an independent parameter here, which is the internal heating rate. I've called that chi on this image. So just back to the boundary conditions. And so all the models we're going to be talking about today have a isothermal surface boundary condition, T-surf. For the most part, I'm going to talk about models that have an isothermal basal or core mantle boundary condition as well. Some models we'll look at by other authors have insulating boundary conditions. There's good reasons for specifying insulating boundary conditions under some circumstances. And then for mechanics, we specify free slip boundaries at the surface and at the core mantle boundary. So the contact with the core and the contact with the oceans and atmosphere don't apply tangential stresses to the mantle. And I've also put this star next to the viscosity, right? So that's because most of the parameters we can consider here are going to be designated as constant valued, but viscosity is much more complicated than that. So I'll talk a little bit here about the viscosity models. Whenever I see a talk, I like to see a few equations, so I thought you guys might feel the same way. I've laid these out for a few reasons. One is these parameters we've just talked about, they're incorporated in practice because most of them roll into something you may be familiar with called the Rayleigh number. And what we actually solve in most calculations is a non-dimensional set of equations, conservation of mass, momentum, and energy. And within those non-dimensional equations, the parameters I mentioned on the previous slide end up being incorporated into the Rayleigh number, which appears in the momentum conservation equation if you've used a diffusive time scale for non-dimensionalization. And in the non-dimensionalized internal heating rate, H, okay, so that chi value, if you remember, was the dimensional internal heating rate. So that'll be due to things like uranium, potassium, and thorium in the mantle. And of course, we also need an equation of state. So the really fundamental or most important thing we have to worry about or focus our attention on from modeling plates or trying to generate plates is the viscosity. And the viscosity is designated here as a function of temperature, depth, which I've called R, so the radius of the planet, if you like, and the strain rate, so epsilon dot. So for the thermal dependence, the critical thing is that the viscosity is exponentially dependent, in fact, on the inverse of the temperature. I'm showing an equation here for what I use in my own models, and I think a few of the other calculations I'm going to show you some results from by other authors have used the same formulation. I won't guarantee that every author has used this exactly. We use this form for the most part that is what Paul Tackley described as being Arrhenius-like. It has a 1/temperature plus 1 dependence, where the EA is the activation energy. So it's the specification of the value of EA that actually determines the total viscosity contrast due to temperature in the models. In order to get anything that looks like plate boundaries or allows motion at the surface, as we'll see shortly, you need to specify something called the yield stress and allow for the viscosity to respond to the strain rate so that there is a weakening at the surface. And this yield stress function, it can be a function, can be made depth dependent. It is in a lot of studies. And for the cases I'm going to show you today, however, I'm going to stick to results where a constant value has been specified for the yield stress. I'll also just note that this epsilon dot in the definition of E to yield is actually the second invariant of the strain rate tensor. So that's a scalar value in the cases that we're going to examine here. With this, allowing for these dependencies of viscosity on temperature and on the strain rate and also on the depth of the mantle, we end up with this sort of composite viscosity that is actually what appears in that equation I showed you on the previous slide, the viscosity appearing right here, okay, in the momentum equation. So I just want to point out also that not everything I'm going to show you allowed for a viscosity response to depth. Now, most of the cases where this is incorporated, the primary thing that is being included here is some sort of a factor in increase in viscosity in the lower mantle. So as soon as you go across the 660-kilometer discontinuity, there is a specification of a viscosity jump, which multiplies the temperature dependence of the viscosity. In the models from my group, we use a factor of 30 here, and I'm happy to discuss that at the end if anybody has any questions. The key thing, though, about this, just to bring your attention to it, is that if the viscosity due to temperature or the viscosity due to the stress or strain rate, however you want to think about it, becomes particularly low, then this formulation ends up dominating the total composite viscosity, so it will become very low, whether the temperature or the strain rate part demands that. So here are some results from, excuse me, one of the first studies to incorporate yielding into a 3D spherical convection model. It's by Hein van Heck and Paul Tackley back in 2008. And the first thing I want to bring your attention to is that if we have a very, very high value for the yielding, in other words, the yielding doesn't really take effect, then we end up with what some of you may be familiar with as stagnant lid convection. That's what's shown in the top row of these figures, right? And it's worth keeping in mind that the activation energies for the mantle constituent minerals will imply that the thermally activated viscosity variation extends by more than a factor of 10 to the 30 across the Earth's mantle. Now, in general, that is not what is specified in the numerical models. Values of order, let's say about 1 million, sometimes a little higher, sometimes a little lower than that. Okay. But again, if we don't have yielding, then due to the response of the viscosity to the cold temperatures, we'll end up with a stagnant lid. Now, with the incorporation of a yield stress that's much lower, we can get things like what are shown in the bottom row of this figure. we can get weak bands developing that allow for divergence and convergence at the surface so that the surface can end up in motion. The other thing I just want to point out about this particular study was it employed the insulating boundary at the core mantle boundary, so it doesn't include any plumes. Now, you have to make that allowance because of the convective vigor here being much lower. If you have an effective Rayleigh number that is low, then the plumes associated with that sort of convection are so large in scale that they end up breaking the surface and sort of come to dominate the convection as much or more so than the downwelling. So that's one of the reasons at lower Rayleigh numbers, if you go back and look in the literature, there's often the employing of an insulating boundary. Now, shortly after that study came out, there was a follow-up study by Brad Foley and Torsten Becker, appeared in 2009. And they had a look at some higher Rayleigh number calculations, so slightly more vigorous convection and a slightly thinner outer thermal boundary layer, so what we would equate with the plates. And they also found that they could get weakening and that they could get surface mobility. And the critical thing here, though, is by changing the boundary condition from being an insulating condition to a isothermal condition at the core mantle boundary, it changes the entire effective temperature structure of the system, which means it affects the viscosity throughout the system. And that has implications, for example, for the generation of plates, because if you've just discovered, let's say, what kind of a yield stress may give you surface motion with an insulating boundary, because that's tied into the viscosity determined by temperature. When you change the boundary condition at the bottom, you change the viscosity throughout, and so you're going to need totally different sorts of yield stress values to generate plates because of the change in the core mantle boundary condition. A little bit, this is jumping forward a little bit now to a 2016 study. Claire Millard's work with, Claire's working in Nicholas Coltise's group. These are now much more vigorous calculations, or the convection is much more vigorous in these cases. And Claire is showing a sort of the effect of systematically increasing the yield stresses here. Right, so we've gone from 100 megapascals all the way up to 250 megapascals. There's 2 points I want to raise here. One is because the convection is so much more vigorous than in the earlier models that we looked at, that plumes aren't really going to dominate these systems the same way that they would with a lower Rayleigh number. Right, so now we can see that it's really a focus in this set of figures on the impact of the yielding. So for the 100 megapascal case, it appears that the surface here, she's plotted the dimensional viscosity in the top row. There's a lot of weakening, which shows up as the red and the yellow in the viscosity field. The green are the strong regions. And as the yield stress is increased, we start to see a greater focusing of the weak regions. And as it's increased even further, we start to see a division so that there are very clear and distinct regions that are surrounded by weak bands. And you can assume, therefore, that perhaps this is an indication of the formulation of something like plates. And the higher the yield stress goes, of course, the larger the plates become, because the weak bands become more difficult to generate with the higher yield stress. And in the limit that we keep increasing this yield stress, we're going to get back to a stagnant lid state, as we saw for that earlier study I was showing you from Tackley's group. So let's just stop and return to a couple of those questions I asked before about when has a mantle convection model generated plate tectonics. Well, the foregoing results, it seems that at least weak bands, the first requirement for obtaining plate boundaries, can be obtained with this sort of a yield stress formulation that we've been talking about, coupled with an exponential dependence on 1 over the temperature, or 1 over the temperature plus some sort of a offset temperature. So the questions now turn to refinement and verification. That's what I'd like to focus on for the rest of this presentation. And the first thing we might ask about is, can we obtain the dichotomy that exists in the Earth's plate boundaries? So what do I mean by dichotomy? Well, I'm referring to the fact that the divergent and convergent boundaries on the Earth differ in their form and their thermal structure. So this is a figure of ocean floor age taken from one of Dietmar Muller's group's publications going back to 2008. And just a reminder that if we look at the divergent boundaries at the Earth's surface, where we've got spreading boundaries on the surface of the Earth incorporate these offset segments where we get, they're dominated by shear, and those, of course, are the transform faults. And in contrast, convergent boundaries, oceanic trenches associated with subduction, they're arcuate or arc-like in nature. They don't have this intermittent behavior where they, or character, where they incorporate these offsets along the boundaries. So can we generate this? Well, the short answer to that is yes, in some cases. It seems like it is possible to generate transform-like offsets. This figure is from a group from my research group in Toronto. This was published in 2021. And what we're looking at on the left, again, are plots of viscosity from a snapshot in time of a single model. There's a 180-degree change in the viewing angle in these top rows and bottom rows. So they're sort of diametrically opposed viewing angles. The right column is showing you the divergence of the surface velocity corresponding to the viscosity plots in the left. And you can see that where we've got positive divergence, the red, that there are a number of offsets that have been generated along the boundaries that appear in this model. In contrast to where we've got convergence, the blue, where there aren't offsets, and we have these arc-like features once again. So now the reason that this may appear is that these models have a thinner thermal boundary layer than a lot of the previous results I showed you, or results in the previous studies I show you. So thinner plates may be absolutely necessary in order to try to, or to have a chance at seeing these transform-like boundaries emerge. The other thing I want to mention is that I won't tell you for a moment that these boundaries appear with offsets in them all the time. We did find that in this study that this can be intermittent, and the degree to which the boundaries will appear can vary. So sometimes at a particular snapshot, we may see something like 30 different offsets, and another time we may only see 2. But generally, we can get some offsets for the conditions that are included in this model. So let me just go over what that is. So we have that factor of 30 increase in the lower mantle viscosity relative to the upper mantle. And that's because of the change in the mineralogy and the inferred change in viscosity that goes with that change from, I guess it would be Wadsleyite and ringwoodite into bridgmanite in the lower mantle. We've specified here a activation energy so that we have a total viscosity contrast due to temperature of 3.2 times 10 to the 6. The model includes internal heating and an isothermal core, and we've specified a yield stress which has a dimensional value of 110 megapascals. For those who are interested in this sort of thing, the Rayleigh number at the core mantle boundary would be 10 to the 9, just based on temperature. But when you multiply that by the factor 30 increase in viscosity due to depth, the core mantle boundary Rayleigh number is 3.33 times 10 to the 7, the surface value is 3 times 10 to the 2. I've also just stated here the resolution of this model for those, again, keeping score on that sort of thing. That comes out to be something on the order of about 30-kilometer resolution. As far as what the interior of that case looks like, I thought I'd show you a couple of snapshots here. So for these, we've on the left, I've got 4 snapshots from different viewing angles, all at the same time, right? The left is the temperature. The right column, again, is the divergence field for the surface velocities. And the larger figure here then is the top row. It shows you if we sort of peel off the lithosphere, if you will, the cold upper thermal boundary layer, what's going on underneath. And we can see that there's sort of these sheet-like downwellings that are descending below those convergent boundaries, wherever convergence is shown at the surface. And then these yellow bands are where we've got the highest divergence at the surface. And the main point of just showing you that is to point out that there aren't any deep interior features associated with where we find divergence. Okay, so it's not like divergence is above plumes. It's not to say a plume can't interact with one of these regions, but the divergent boundaries for the most part are passive. Okay. Okay, so I said earlier at the beginning of this talk that one of the things I wanted to do as I went through this was make sure we don't entirely confuse the issue of generating what might be satisfying in appearance, at least qualitatively, plate boundaries, with the idea that this means we have generated rigid rotation about an axis through the sphere's center. The thing we really need to do then is to take a look at where the implied plates are and examine those plates for their rigidity. So for that, I wanted to sort of do just a quick review for anyone who didn't know this or may have forgotten this about something called Euler poles. And so this figure was generated by Chad Fairservice. We're first of all in the top row here, just showing what happens. The light gray region is being given a translational velocity around a vertical axis through the sphere. And in the second figure, in B, the rigidly moving cap, the light gray region, has been moved up to the pole, as you can see, and now it's just spinning around the vertical axis. In figures C and D, we've got a sort of superposition of a translational motion around the vertical axis and also a spin that's being applied to the light gray cap plate region around a different axis through its center in row C and through an axis that goes through its periphery in D. Now, in every case, whether it is purely translational motion, purely spin motion, or a composite of the two, it's possible to reduce that to a description of the motion around a single pole, which is rigid motion of the gray cap region around the rigid pole. So, for example, in rows C and D, you can see this axis that I'm referring to is shown with the blue. Right? So the blue is like the composite axis that the plate moves around as a combination of its translation and its spin. And if we take all of the velocities here that we get from these combinations, for example, of the translation and spin, and plot those up as a distance from this blue axis, we end up with a linear plot in velocity, magnitude, distance to the axis, space. So of course, these blue axes I'm referring to are what are referred to as Euler poles. And the nature of the spin along the Euler pole axis, in other words, the magnitude of the spin gives us an Euler vector, right? The Euler vector is parallel to the pole and its magnitude is determined by the spin rate. So the idea in summary here is if we sample all the velocities in the interior of these light regions and plot them up against the distance to the implied blue axis, the Euler pole, we get a linear plot, and the slope of these linear plots gives us the magnitude of the Euler vectors. So the idea should be, if we can identify the plates in our mantle convection models and then sample all of those velocities, we could plot those up similarly after having found a statistically determined Euler pole, and we should expect something that looks like these linear plots. So I'm going to go back to the same idea here of 3 models with different yield stresses. I showed you something very much like this in Claire Millard's work. This is from our own study. This was actually from Sean Langemeyer's thesis. And now we are again, just everything is kept constant in these 3 models, right? So each column here is one snapshot of one model. And we've got 6 different viewing angles in the rows as indicated by the coordinate axes that are shown. And we've plotted up the temperatures at a depth of 9 kilometers below the surface using a logarithmic scale. So we've done that partly for the fact that the logarithmic scale helps bring out the fact that the very old part or coldest parts of the surface show up much more light blue, and some of the younger parts of the surface show up in a darker blue. So that helps us to see where we've got convergence, for example, as well as the obvious divergent boundaries, which are showing up with this sort of glowing yellowy red color with the color palette we've used here. I also just want to point out that it's the middle of these yield stresses that is that case I showed you earlier where we get these offsets, the transform faults appear in certain places. This is a different time from what I showed you in the earlier slide, but it's the same model. Okay, so we're going to examine these 3 cases and take a look at the rigidity of the implied plates, right? So the plate boundaries appear to be somewhat easy to identify in some of these cases, maybe not other places. Like it's difficult here really to say where the boundaries should be when the yield stress is lower. But if we can find the plate boundaries, then we can sample all of the velocities inside the plate boundaries to see how rigidly these implied plates are actually moving. So we use the same, well, actually, it's from a different paper. We use a software package that was developed by Claire Millard, working again with Nicholas Coltese. This is found in the literature under the acronym ADOPT. It's the Automatic Detection of Plate Tectonics, ADOPT. And what we're showing in this figure, which is from a GGI paper that my group published last year, is our different interpretations of where the plate boundaries are in those 3 models I just showed you with the 3 different yield stresses. Okay, so we can see, for example, with the lower yield stress, the plate boundaries are, there are many more plate boundaries, for example, on from some viewing perspectives, and interestingly enough, there aren't that many plates inferred from this viewing angle in the top row, but there are many, many plates found with the lower yield stress down in this 3rd row and so on. So there are a lot more plates, as we described earlier, when the yield stress is low. If the yield stress is really increased to a high rate, you don't get many plates at all. We end up with about 6 plates in that case. And somewhere in the middle of this, for an intermediate yield stress, we end up with the plate number sort of flipping from time step to time step from maybe 16 plates up to, let's say, 20 plates. So having identified these plates, we can now ask the question, well, if I sample all the velocities in the interior regions here, like of this plate 1, and then I plot, I find the statistically implied or inferred Euler pole for that, and then plot those velocities versus distance to the Euler pole, will I find that these plates are moving rigidly across the surface, meaning I should get a linear fit. So here's the first case, and it doesn't look very impressive. These are the 6 largest plates from the model that had the lowest yield stress. We use something called a threshold in order to find the plate boundary. So for the moment, I'm going to just tell you we use the same threshold value for all 3 of these cases. The threshold value is something that gets fed into the plate boundary detection software. Okay, so we are plotting again all of the velocities versus distance on the horizontal axis to the Euler pole that is implied by statistically inverting all of these velocities to find a single Euler pole. And as I showed you in those sort of synthetic examples a few slides ago, these should all be linear. In other words, all of these, every one of these data points should be lying on the red line, which actually it corresponds to the rigid motion around the implied Euler pole. So it doesn't seem to appear to work very well for this case with the low yield stress. If we jump up to the case with the highest yield stress, it's not a lot more encouraging. There is some indication of something that's working at least, or something's at least organized. You can see maybe for this red plot that things are trying to fall along a line. The yellow one looks like it's a combination of things trying to fall along 2 different lines. The pink isn't bad, but isn't great either. Now, that intermediate case, of course, is the reason I've got something to talk about today, because actually we do find pretty good linear fits, all things considered, for a number of the plates in that case with this particular threshold for detecting the plate boundaries. You'll notice, of course, immediately that the data corresponding to the black plate, the middle column upper row, doesn't look like it wants to play the same game as the others. And I'm going to argue here that, well, the reason for this is because the automatic plate detection software is trying to lump together far too much of the surface into one plate. Let me just go back to this slide, right? So this is this plate 16 on the surface that's not working very well. You see it's a very large region compared to some of the others. I'll just get you to also look at 13. Okay, so 13 was one of the ones that works quite well. So that region does appear to be moving somewhat rigidly around an Euler pole, right? So we'll just go forward a couple of slides again, and right, so there's 13. It works quite well. 16, not so much. So we can ask the question, well, perhaps we've just picked the wrong threshold here. We're trying to lump together too much of the surface into one plate. These are now 3 Mulvide plots of the surface for different threshold values, where we are looking at just the one case for the intermediate yield stress, right? Remember, we had 3 models with 3 different yield stresses. But now what's being varied from the top to the bottom are using different threshold values in the plate detection software. So you can see that as we lower the threshold value, and these, by the way, for people who are familiar with it, are using a watershed algorithm. As we lower the threshold, it finds more and more plates, right? So it finds plates to the point where you can say, okay, enough already, I've got too many plates. So let's just take a look, though, again at that plate 16, the black one, right? So that was the one that gave us a really not very convincing rigid behavior. If we get a little bit more specific with the threshold so that we can divide that plate into a few more and then even more plates that will pop out, we can have a look at what the implied rigidity is for each of these individual regions by finding their unique Euler poles or their distinct Euler poles. And that's what we've done here in two examples, right? So here's that black plate again, plate ID 4. It is here because of that's actually plate ID 4 for threshold 30. I know I call it, I think it was 16 for threshold 20. So I've gone and changed the number on you. Sorry about that. We can break that up though if we go to threshold 10%, and we can see that that large region is actually a composite of 4 individual parts that are moving more rigidly individually. Similarly, the large green plate that we had in the previous slide here, this green one that stretches around, we can see that as we break that up, it becomes this sort of tan colored and green colored and purple colored plates as it's broken into segments. And when we take a look at those regions distinctly, we can see that they also conform much better to rigid rotation around their own Euler poles. So one of the big issues here is just finding the right threshold to find the plate boundaries. It sort of seems like an obvious conclusion, but the problem is, how do you find these boundaries when you don't have anything in a convection model to go by? You don't have any seismic record, you don't have any paleomagnetism or other geophysical observables to help you get the correct plate boundaries. Okay, so let's just summarize then what are some of the problems we've identified trying to play this game. So lowering the threshold disassembles multiple regions that should be treated as a single plate into multiple small plates, right? We don't want to necessarily keep breaking down a plate into smaller and smaller fragments once we reach some sort of, let's say, optimal size for it so that it is moving more or less rigidly. So this algorithm also adds and removes what I'll call the borderline plate boundaries from one time step to the next, which is very chaotic if we want to do anything like tracking the time evolution or the history of the plate velocities and the Euler poles. So we're sort of at the issue now that we have to select the best, which is kind of a Goldilocks issue sort of threshold in an optimization problem. And what I'm referring to here when I say we've got a bit of a Goldilocks problem is like we don't want the threshold to be too high, because then we force large regions to become part of the same plate when they shouldn't be. But if we go too low, we end up splitting large plates that are, for the most part, moving rigidly into many small plates and can't really get a read on what are the largest units that are moving rigidly. So to try to tackle that issue, we introduced something called the deformity field, which I'm showing you here. These are the same projections, the Moleweed projections, with the different thresholds that I've been talking about at 30%, 20%, and 10% threshold. The deformity field, as is described here, is a calculation of the plate velocity or the actual model velocity, the absolute value of that minus the absolute value of what the velocity should be if the plate is moving rigidly around the inferred Euler pole, and then divided by the sum of those two things to normalize it. So the idea becomes that if you get a value of 0 for the deformity, which will be green, then that means that entire plate region is moving perfectly. It rotates rigidly around its Euler pole. If we have these yellow regions, well, what's happening is that the actual velocities are exceeding those expected for rigid rotation. And the blue are places where it's vice versa to that, right? So the rigid rotation would imply a greater velocity than what we're seeing. So we could say, well, what if we iterate on this deformity field by changing the threshold values here? And then we look for something which is, let's say, suitably, I'll say in, air quotes, green. And then we've got mostly rigid rotation around the surface for the plates that we have identified. So just to summarize what we've discussed here is a few shots or a few renditions of these large plates with the corresponding velocity arrows shown on the surface. and the plots of the velocities versus the distance to the inferred Euler poles for all of these. You can see quite a lot of them do give pretty good linear fits. So I would argue we are producing a fair amount of rigid behavior on the surface here. And also I'll remind you of something I said very close to the beginning, which is that even the real Earth does have probably today around 15% of the surface not really conforming to this rigid behavior around an Euler pole. We have diffuse plate boundaries, regions, interplate regions where we have deformation and so on. So this does appear to be somewhere on the, let's say, the right road towards generating rigid plate motion from a mantle convection model. At least I hope I'm convincing some of you of that. And I'm just keeping an eye on the time. Let me just wrap up with a couple more slides. I'm going to skip these things, and let me talk about this one for just a moment before I get to conclusions. If you're wondering how this method works when applied to the Earth's real data, we've applied this method here to the online data for global strain rate that was published by Creamer et al. In 2014. And the findings are actually very similar to the geodynamic model output, which is that if the thresholds are too high, we miss some boundaries and combine some plates. And you can see that, for example, here with the highest threshold, which is shown in this column. By the way, I should have mentioned that the rightmost column here is the strain rate data. Okay, so we've got 3 different thresholds, once again, of the adopt value threshold for finding the plate boundaries. And if the value is too high, then the software does things like trying to combine the Pacific plate and the Antarctic plate and the Australian plate into one giant plate, which does not, of course, rotate very rigidly under those circumstances around a single Euler pole. So many of the things we saw in terms of using the software in the geodynamic models works exactly the same when it's applied to the real Earth data. So I have a few more slides here, which I'm going to skip going over today. For anybody who wants to talk to me later in the week, I can talk to you about evolution of the plates that we can detect and building Euler pole histories and looking for events like reorganization events in plate tectonics. That's what we're working on right now. Let me just finish off though with some conclusions based on what I've talked about here. So assessing the success of plate generation in spherical mantle convection models requires not only striving for obtaining qualitatively assessed narrow bands of surface deformity, but also quantitative assessments of rigid plate motion. And we've presented results from a model that intermittently yields transform faults and show that the majority of its surface moves like distinctly rigidly rotating caps or plates. This rotation occurs about Euler poles that can be statistically determined. Nearly rigid plate motion can be generated over the majority of the surface of some of the systems that we've modeled. And I'll leave off there. And thanks for listening, and I can take any questions if you have some.
Amazing. Thanks so much, Julian. That was a great talk. If folks have questions, why don't you go ahead and raise your hand, and you're welcome to just unmute yourself and ask your question, or you can type it in the chat, kind of whatever folks want to do.
I have a question, Julian. I thought it was a really interesting talk. Thank you. I am curious if if it's possible to kind of go backwards, right? To take the strain rate for the modern Earth and then, essentially run the model backwards and see if you going from the modern plate geometries get what we know previous plate tectonics did from the model. Does that make sense?
I think it does. So you're asking, can you run the convection model backwards?
Yeah, basically, would it be possible to take the surface, the surface strain from the data that you were fitting with your plate recognizing algorithm, and then have, I don't know, some constraint like topography or something, and then the convection model and run it all backwards.
So people have tried to do this sort of thing, I would say 20, 25 years perhaps. Peter Bunga, I don't know if you know Peter's work at all. He worked on this sort of thing for a while. I think some others have too. You run into a couple of problems though. You can't run diffusion backwards. So there's a very limited lifetime for which you could try to run a convecting system back in time because you're trying to undo diffusion.
Sure.
The other problem you have is, which is none of the, I will say that none of the results I've shown you are actually modeling the Earth with the Earth's convective vigor. So you could say, well, what do you mean by convective vigor, right? Like I alluded to Rayleigh numbers, for example. I think probably the best way to think of convective vigor or how to measure that, though, is like the thickness of the upper thermal boundary layer, right? So if we say, okay, well, the thickness of the upper thermal boundary layer for the Earth is of order 100 kilometers, that's sort of plate thickness or slab thickness. If you look at all of the cases I've shown you, those higher Rayleigh number ones from my group from a few years ago that we published, they're probably still on the order of a Rayleigh number, which is maybe a factor of 5, possibly even more, too low for the Earth, which means that our plates are all too thick. And the limit there, of course, is that, well, it's computational. How, for as long as people have been playing these games, we keep trying to push the limit on getting to the Earth's parameter values so that we can generate Earth-like output dimensionally, that we do get plates 100 kilometers thick, that we get the right sort of heat flux out of the core and so forth. But we're still not quite there as far as what we're really modeling. And also, do you remember the slide I said, well, actually, if you really plugged in the right activation energy for the Earth's mineralogy, the viscosity contrast is of order about a factor of 10 to the 30. So we're modeling, and it's an amazing number when you actually plug that in and think about what's implied by the activation energies. So you would need, so these models include viscosity contrasts of order 1 million, which is pretty high and quite demanding numerically. I think other people have gone higher. I mean, right now, actually, we're running at a contrast around 100 million in our latest calculations. But it's all still so far off of what you really need for the Earth to model the Earth that, and not to mention the diffusion problem, that it's really forbidding at this point to think about going and taking the current day and going back in time. But if you could do it, I think there's sort of still a limit there of maybe 100 million years maximum because of the diffusion problem.
That's super interesting. Thank you.
I guess if I could just add to that, I know there's a question here, but just to follow up briefly on Craig's question, I think it's a really good one. And as Julian said, people have time reversed convection, but almost everybody has done so by pushing the plates backward, which assumes you know what plate tectonics is doing. And very few people have actually tried to explore the consistency of the evolution of plate boundaries. And I think that's really interesting. Nico Coltis and his team, they did something that goes along those lines. So they've sort of pushed things around, hand of God, and then everything is sort of nicely evolving. And then they take off the hands and things move forward. And it immediately falls apart. So if you say, like you do everything up to say 20 million years ago, and then you would assume that at least moving forward from 20 million years ago to the present day, the convection model would do something, you would think like those are minor plate reorganizations, and it looks nothing like what actually happened. So, and I don't really understand why that is, because of course these convection computations like the one that Julian showed, they're inherently self-consistent. And if we set up things like, say, we know where the plate boundaries are, and we attribute some viscosity and some density distribution, plates move the right way. So on the one hand, we feel like we have this understanding that we understand that we like things balance out, how plates are driven. On the other hand, it seems like the evolution of plate boundaries is completely wrong still. And I guess um, you know, uh, one way to ask this, which is also going back to your question, is if you look at the places where there are these large deviations between the rigid Euler pole motion and what you get, Julian, where do those places lie, right? So you would assume that the plate is getting squished, so then the plate boundary is going to reorganize. Have you looked at sort of the spatial distribution of intraplate deformation? And then sort of immediately, right, thinking about the Earth, when you look at the present day, most of the interplate deformation is within the continents because stuff's weaker. And that's not in these models, right? Because Julian, you've shown models that are purely sort of oceanic lithosphere, right?
Yeah, so I very conveniently didn't have a slide in here about all the caveats. But that's one of the biggest ones, right? There aren't any continents. This is purely oceanic plates, the way we've described things. So I mean, that could be a really critical thing. I guess the one place where I could have gone back and said, oh, well, here's some continents, is what I skipped over somewhat quickly with the real Earth data, right? I found this very interesting, actually. When we applied this same adopt software to real Earth data, it finds all the regions of orogenesis, for example, and says, oh, well, these are like mosaics of hundreds of little plates. You know, like here's the, if you can see my cursor, I assume you guys can.
Yeah.
This is like the Himalayas, and you know, you can see this same sort of thing along the Andes and along the Cordillera in North America, like anywhere where there's mountain building, it wants to put in lots of little plates with this software, right? So clearly, these fields have lots of deformation. The fields associated with mountain building in the real Earth data. Something that could be very important for the generation of plates here, which has been explored by Tobias Rolfe with Nicholas Coltese, I think, was that by including continental lithosphere in the models, it can change the value that you would need to generate plates in terms of the input yield stresses. So you can go with much higher yield stresses if you include continents, and the continents will take up some of the or allow for some of the deformity that you need to happen and for the stresses along their margins. That could be something else that could take us in a direction towards, again, towards models which are potentially needed in order to match Earth observations. The other thing, though, which I was thinking about what you said, Torsten, which is something else my group's working on, but I haven't touched on at all here, is as soon as you put in anything like a chemical constituent to model LLSVPs, that this affects the global viscosity. This affects the viscosity throughout the mantle. And so if you don't really know the details of what's producing LLSVPs, that alone can act as something that will change the evolution of the system by impacting the viscosity throughout its entire structure. I mean, the LLSVPs are acting similarly. If they are chemical in nature, they're acting similarly at moving around over the CMB to what the continents are doing moving around in the lithosphere. And they're changing the temperature and therefore the viscosity throughout the system.
Cool. Just real quick, I'll throw in that it is 3 o'clock, so if anyone has to head out, feel free. I'm not busy, so I'm happy to keep the Zoom open for a little while longer.
There was one online question, which because the hand is down now. We've been yapping too much.
I think I see it. It's John.
Yeah, that's me. Thank you. Enjoyed the talk. I just have maybe 1 or 2 questions about the adopt. you showed the picture with the really beautiful like downwelling sheets, which seems really like indicative of a boundary. Does adopt always, you know, are the boundaries that are present kind of like structurally in the model easier to pick up for, or are they always picked up by adopt, or you know, what boundaries does adopt miss first when you, I guess, raise the threshold?
So actually, it's a complicated question, John. And adopt is not really ideal in the sense that, you know, it uses this watershed algorithm, and we apply it in our use. You can use any field you want as input to adopt. So you could use viscosity, let's say, or you could use the temperatures. We choose to use the strain rate data. So for example, that's what's shown in this right-hand column. And as you can see in the center column here, these are the boundaries that adopt is saying it confined with this watershed algorithm. Now, if you take a look at plate 5, for example, it's very clear in the strain rate data that some of that focus boundary pops right out. But then there's this sort of big diffuse region where I've got my cursor right now, and you can see that adopt sort of cycles through that and says, okay, I think going through there, there's a boundary through that because there's definitely weakness. And this is where I think the boundary is. And this is where the threshold value that's fed into adopt becomes a little bit questionable in terms of, well, how good is it in terms of finding those boundaries that are not so well focused? Right now, something I'm potentially going to talk about Friday morning, I don't know if that is going to happen or not, is that my group's actually working on abandoning adopt and using a completely different tool. And I have a slide here quickly. And what I'll just show you here is that we are now calculating, these are very similar to what I've been showing you throughout, you know, like this stacked field, for example, is a combination now of strain rates and temperatures. We find the plates that are shown in this next column, but what we're able to output now is a probability that we've put the boundary or the surface region with the correct plate because of these sort of diffuse regions that are difficult, as I described before. I mean, there's a good example here in the 5th row, right? Like, what do you do, or what does adopt think it's going to do to connect across here? If it says this is all one plate, then it just doesn't move as one plate, but finding the actual boundary is difficult. So the new software says it's in this region, and I can give you the probability of each of these locations being the actual plate boundary you're looking for. So I don't know if that helps, but if you want to talk about this later in the week, I'm happy to do that.
Thank you very much. Got it. Thanks.
Yeah, Chow, go ahead.
Hi, Julian. Great talk. Thanks. I just have a quick question. So you have a slide showing, you know, you use three different values of the yielding stress, and ask like which yielding stress would generate the transform type of boundaries. Like, how expensive is one simulation? It seems to me it seems to me like quantify that range may be useful. But you just have three values, and the one in the middle, which is 100 megapascal, generate that type.
Yeah. So the answer, I guess, in terms of expensive, so the first part of that is I've come to realize working with Torsten that we don't have anything like the computing facilities that you guys have with Frontera. But so when those were run in, I guess 2019 and 2020 was when we did a lot of those computations, and they took several months, but only running on 32 processors. So we were running, I think Sean had about 13 models in his thesis, and it took him about 2 years to get those results, the 3D results. And that was each running on 32 processors. Where you spend a huge amount of the time though, Chow, is in trying to get the system to thermally equilibrate so that you're not just analyzing some transient feature. You know, sometimes it takes sort of 2 months of running the job to get it to settle down to something statistically stable. And then the actual period you're interested in, maybe it's just a 2-week run.
See.
So I did mention that we've sort of got like a new generation. We're getting a new computer in Toronto that's currently scheduled to come online in April. They've just mothballed the one used for all of these calculations. And we're also using what I think is a much better viscosity formulation going forward, as well as having been working on this new plate boundary detection software. So yeah, I agree with you though. It'd be really nice if we could spend more time trying to look exactly at the yield stresses that'll give you long-term transform faults.
Yeah.
But I think it's
I guess I focused a bit more, to be honest, on trying to push the Rayleigh number higher, because I feel like the Rayleigh number is probably the critical thing more than I think there might be a range of yield stresses that would work if we could get the plates thin enough.
Yeah, but I mean, just to be clear, there has been some exploration of parameter space, but it is somewhat tricky to do for these large computations. So there's but I mean, Julian might disagree with this. It does appear that the range over which this plate tectonic-like behavior is achieved is fairly small.
I agree 100%. Actually, I think that was on a slide, but I didn't dwell on it, and I just sort of gleaned over that point.
Okay, thanks.
And there seems to be, I guess, based on the existing studies, it's not that the Rayleigh number widens the range dramatically. I'm not sure if you've seen this, Julian. There's been a paper by Chinese author where they fairly recently tried to push things in terms of Rayleigh number and yield stress, and it seems like the range is similar to what people found with the earlier lower Rayleigh number computations.
No, I don't know the paper, Torsten, but
Yeah, I forget the name of the author. It was sort of redoing you know, Foley and Becker at like whatever 100 times the Rayleigh number or something like that.
What journal is that in?
I can't remember.
Okay.
So it was I just came across it because I met someone at a meeting and then I looked it up, but now I forgot. So anyway, but you know, Charles' point is a good one, right? And people have done that, and it seems like the range is fairly small, but it does get tricky because there's this sort of, as Julian mentioned, there's this dependency on the internal temperature, which with it then sort of brings about a quasi-hysteresis where you have to be careful if you come in from the stagnant lid part or the mobile lid part, and it gets messy. And as Julian said, you need to run it for lots of overturns to actually get into the right sort of stochastic regime.
Yeah, it just seems interesting to me that, you know, you choose 3 values and the middle value hit that sweet spot, you know?
Yeah,
sure
so I won't say that. So I won't say we were just throwing blind darts in the blind. What am I trying to say? Darts in the dark. We ran a lot of 2D cases first, so you know, dozens of 2D cases to explore, and then we started running for a range of yield stresses where we thought, okay, we're definitely able to get surface mobility, right? Maybe I didn't make this part clear, but this study did not start by us going, hey, let's see if we can generate transform faults. That was a luck out. You know, it's just like, wow, look at that middle case. Look what we've got here. And I should mention, though, that Nicholas Coltese had a paper, I think probably around 2016, where he described something he said looked like a transient transform fault. And that's sort of all that was said in the paper at the time. Like, he didn't dwell on it. But so, I mean, we had the work of other authors. It wasn't that we chose those yield stresses completely in the dark. And we knew that, well, as I say, what we were really looking for was just mobility and to understand something about actually the size of the plate generation. So like going off of Claire Millard's study.
I see. Thanks.
Okay.
Cool. Any more questions? Yeah, Kashwan, go ahead.
Yeah, thank you so much for very good talk. And I noticed in your equation you didn't include the self-gravitational effects. So I'm wonder if those effects affect your conclusion generally or not.
What effects?
Yeah.
Yeah, self-gravitational effects.
So are we referring to like the value for G in the mantle, or I'm a little unsure what you mean by the self-gravitational effects.
I mean like the buoyancy force was
Oh, the buoyancy force,
yeah,
100.
yes.
No, that's
Mhm.
entirely incorporated, right?
Yeah,
So
yeah, right.
if you go back to the wherever it was I had here, like I remember I had that one slide with the equations in it, right? So I'll just show you where the buoyancy force is in the equations. Right, so the right-hand side of the momentum conservation equation, the Rayleigh number times the temperature, that is coming in the non-dimensional form of the equations, that is the buoyancy force. Right, so for mantle convection, you've effectively, on the left-hand side, you've got a balance between resistance coming about due to the pressure gradient as well as the surface forces, like the tangential surface forces, and then that's balanced by the buoyancy forces, right? What you don't have is any momentum, right? Because it's an infinite Prandtl number approximation. The Prandtl number for the mantle is on the order, I think, of about 10 to the 24. So you don't have to take into account inertia or well, you don't have to take into account rotation either.
Yeah, right. Yeah, right.
But you have this.
But
Yep.
I think part of my question maybe not related to this, but yeah, I think the Poisson. So you don't have you don't need to consider the Poisson's equation, right? Just like the gravitational potential, they need to.
Yeah, Keishan, you're thinking about the geoid, right? Where the
Right.
is
Yes.
important. But
Yeah.
here, this would just be a very tiny variation in G, but that's not significant.
Okay.
Yeah, so we do like we assume the Earth is a sphere, not an oblate spheroid. We don't take into account anything. We don't have to take into account Coriolis forces or centrifugal forces because of the high Prandtl number.
So you can actually show that the ellipticity and the centrifugal force have a tiny effect on which wavelengths are selected at very low Rayleigh numbers. So there is a subtle effect, and this might actually be important when you think about the other way, about the solid Earth, the solid core freezing in before it's fully frozen. The ellipticity might actually affect the sort of convective patterns you get, and that might affect inner core anisotropy. So if you have really low Rayleigh number, those effects might have a tiny effect, but for high Rayleigh number, it's irrelevant if it's elliptical or if there's slight changes in G.
All right. Any more questions? Yeah, go ahead.
Hello. Thank you, Julian. Thanks for the talk. And I just wondering what kind of initial temperature conditions in the model you use, just like whether or not you just include the random perturbations temperature in the model or just like others.
Yeah,
things.
that's a great question, Jiang, because I didn't talk about that at all. So there's a really long history to these calculations in the sense that the way we've run them, this goes back to an earlier question I had about how long does it take to get these, to finish these. We started off with a lot of 2D cases. You can start the 2D cases with fairly simple setup, like, as you say, like a random perturbation for the, and then you specify the rheology you're interested in. You run that forward in time. You may have to start with conditions that are at a lower Rayleigh number and you gradually force the Rayleigh number higher. And the reason you do all of that is for numerical stability. And you run those 2D calculations, let's say, until they've reached a statistical steady state at that point. That gives you some information now about what kind of temperatures you might expect with that particular set of values for the parameters you're modeling, right? So now you could take the temperature profile from the 2D case, specify it as your initial condition in the 3D case, specify all of the same parameters, and then start running that again. And now that's when you get into the situation that I described where it's like, okay, now you've got to be patient and run that 24/7 for 2 or 3 months until it's become equilibrated. So you have a very long time series. I mean, we've just been running some models like these, but also including LLSVPs, and they've taken about 4 months to equilibrate. So the answer is that what I'm showing you here are snapshots that are sort of taken somewhat randomly out of very, very long simulations, running months.
Oh,
The
okay.
3D and the 3D initial conditions came from running 2D models, first of all.
Okay.
I mean, the way
Thanks
to
for that. Oh, sorry.
first order,
Um,
right? The way to think about it is in terms of overturn times, and
Yeah.
you need to have a lot of those to mix it up. And if you were to start with random perturbation, it's gonna take forever to spin up, and then you have to wait for the overturn times. That's why we often start with some sort of other model, as Julian said, lower Rayleigh number or something like that. But then you have to be really careful that it's consistent with the surface boundary conditions if you have these viscoplastic rheologies. So it's a real pain to
Yeah.
to ensure a statistical steady state.
Because you also want to use the 2D model or the 2D study, first of all, to kind of nail down what the parameter values are you want, because you want like you may say, okay, well, look, I want this percentage of heat to be coming out of the core. You
Right.
don't know a priori when you start up the model, how much heat am I going to get out of the core once it reaches this statistical steady state? And you say, well, I wasn't interested in a model that had 90% of the heat coming out of the core or 2% of the heat coming out of the core. And I also wanted to make sure that I didn't end up in the stagnant lid regime, or contrasting that I don't end up with 30 plates, that sort of thing. So you go through all of this sort of trial and error with all the feedback that exists in these systems in 2D, where it's not too expensive, as well as reading what other people have already told you about what worked and what didn't work. And then once you think you've found the right regime space, you just got to sit down and be patient for a couple of months.
Yeah, I think that truly one pretty great. Yeah, this is a very good method. Um, have you ever tried like inputting the modern Earth's tomography as a density model or temperature anomalies model in your 3D model to generate the plate boundaries?
I've never done that, but many people have. There's a whole sort of literature, I guess you would say,
Yeah.
where people are taking real Earth tomography and converting it into temperature fields or density fields somehow if it's thermochemical. So no, I don't do that, but other people do.
Oh, do you
You
think
run
your
into you
model?
run into this,
Yeah.
many of the same issues I mentioned. The very first question I had, I think, was somebody asking like, well, what if you took the current observations of plate motion and you applied that to a convection model to try to learn something about the interior? It still comes about to, like, you have to have such enormous faith that everything you're specifying in your model doesn't include any of the idealizations that we're actually including in these models, right? Like, I could sit here and start to tell you all the shortcomings of the calculations. Obviously, I don't really want to do that. I mean, other than just to say, well, yeah, of course they're there. I mean, we could talk about things like compressibility. I've used everything I've talked about here has a Boussinesq approximation. Compressibility could be important. Activation energies aren't correct here. We also don't worry about an activation volume, which you have to with compressibility. We don't have phase changes. So when you want to take, the I guess maybe this is a personal bias of mine. I'm not really big on the idea of taking real Earth observations to try to put them into convection models. I'd rather run the forward models and then compare with the real Earth observations to see how many things can we recover with the things that we confidently can model.
Yeah, but this is an interesting question, Jung, right? So I'm not sure if people have extensively addressed that issue, right? Because what Jung is asking, all right, if things were viscoplastic, right, and we had perfect knowledge of the temperature of the Earth, it should sort of work. We kind of know it doesn't, but it's an interesting question to ask what's missing, right? And I mean, of course, seismic tomography does not image plate boundaries per se, but you could sort of see it working in oceanic lithosphere where we're imaging the thermal boundary layer. And if you had like super good tomography that gives you slabs, then the pull that's exerted should yield the surface in the right way. Of course, the real Earth presumably is not just viscoplastic, but memorizes deformation, right? This is why people have tried to mess around with damage, where once you have damage, then the strength of the rock depends on its history. So then it's not going to work. However, right, what Julian showed is that transform faults appear to arise from purely viscoplastic computations. So if your models are correct, tomography would see it, you can scale the tomography to temperature, then you should be able to regenerate Julian's plate boundaries, right? So it's an interesting kind of thing to think about. And people have tried sort of bits and pieces, but not exactly, I think, what you're suggesting, John, right? Because Julian, if we were to image, like we take one of your models, and then we had perfect knowledge of the viscosity, of the temperature, then we should be able to compute the viscosity, and then we should be able to get the same sort of stuff out, right? So it's interesting to see where and why this doesn't work. Interesting point, I think.
Yes. Thank you.